We study X24Q, the first law of thermodynamics. You can find a PDF file for this lecture by visiting our digital library of K-pop. You type in kpop.org, kpope.org, and there's a table of contents. You click X series, X, scroll down to find X24. The first law of thermodynamics. The main textbook is here. And if you click this K, you can watch the Korean version of the lecture. And if you click the button next to E, you can watch English version of the lecture. If you click here in the middle, you go back, return to the digital library, kpop.org, and at the end, you will find the free subscription to the K-pop YouTube channel. So please subscribe if you're interested in, and everything is free. Okay, today we study X24Q. Most subject has been explained in X24 and Q. So let me briefly explain, and you can read it through in details about the discussion. Discuss the work done by the gas during a free expansion and the temperature change. In short, during the free expansion, you must remember the expansion is against the vacuum. So there is no action of this vacuum to prohibit or to hinder the expansion. So the expansion happens without any force against the expansion. Therefore, PDV is always zero. Its integral, that is the work done by the gas during the free expansion, is always a zero. In addition, there is no delta Q, that is the transfer to the heat transfer to the system. So the gas doesn't or loses, does not lose, does not accept any heat. Therefore, delta Q is a zero. According to the first law of thermodynamics, your input and your output and remainder. And because they are all zero, delta internal energy change is zero. As a result, the temperature is invariant. That is very, very important. Next, interpret the following PV diagram of a gas sample. In a PV diagram, P, dV, integral from the initial to final. This one is the work done by the gas. Here, this plot shows that the path of transition is from A to B along this path, and this integral is a positive. In addition, if we choose a different path from A to B, then we will have this area, and this is a positive too. If you subtract this amount from this, then we find the area of the over region. Therefore, in a cyclic process, the area is a positive if the rotation the orientation of the transition is counterclockwise. If the orientation is opposite, then this big magnitude has the negative sign. So this area with negative sign represent the work done by the gas. So this one counterclockwise is positive and clockwise is negative. You have to remember. So when we compute the work, if you know the state, then the P, pressure, can be obtained by N kBT divided by volume. So you insert this. Depending on the system, if you know the temperature is fixed, for example, then this integral becomes a trivial. All right. Anyway, this integral depends on the shape and orientation of the path connecting A and B. For example, this work is still positive but smaller by this than this. Okay? So orientation, both the orientation and the explicit path dependence appears in the computation of the work done by the gas. If you flip the direction, and if you know how to compute the other one in the original orientation, then what you have to do is just attach the negative sign on it. Number 3, explain how to measure the heat capacity CV at constant volume for a gas sample. If the gas sample accepts the heat and keeps its volume invariant, you could have additional term in the first law of thermodynamics. Because V is fixed, this guy disappears, and you arrive at this point. The energy is proportional to the temperature, but there is a certain coefficient, proportionality coefficient, that is called CV. CV is the heat capacity, CV of constant volume. All right, so you can always replace this guy with this. Suppose the temperature of the gas sample has been raised by delta T. Let's see. In that case, the internal energy of the gas has been increased by this amount. Then the conservation of energy, so that's fine. The same gas expands from V1 to V2. Now we have a different situation. Delta V is not zero anymore. Therefore, our original input, the delta T has been raised at a fixed volume, constant volume. That is our original constraint. So amount of heat was this. But now we have changed the situation by allowing the change in volume. So the first law of thermodynamics should be written in a full form: the energy, internal energy change, and the work done by the gas. Now, the temperature, this was the old temperature change when this volume change was missing. However, because this gas could work, the temperature should be different. If a work is a positive, then the temperature increase must be less than previously. If work is negative, if it is shrunken, then this temperature should be raised bigger than the original delta T. Something like that. As a result, we can find the temperature change after allowing the volume change. We just subtract this work on both sides and then divide it by the CV to find this. Previously, the CV was computed with this formula. Okay, the ratio of the heat at a constant volume relative to the temperature change. All right, here delta Q cancels, and the delta T is a multiply, divided, twice divided, doubly divided, so multiplied. Next, number 4, discuss the conduction of heat between a hot reservoir of a constant temperature, hot, and a cold reservoir of temperature Tc, cold. The heat conductor of length L and cross-sectional area A connects the two reservoirs. The thermal conductivity K of the heat conductor is a repeated one, so we can remove this one later. Okay. Why don't we delete this? So, the thermal conduction per unit time is this, from hot to cold. And there is a ratio, temperature change from hot to cold, and distance. And the amount of heat is being transferred in unit time is proportional to the cross-sectional area. So if you widen the area, the heat transfer fast. If you let the length longer, then it takes longer time. Something like that. So we keep this temperature difference, and all of this factor becomes R, just like the Ohm's law. R is resistance. The formula is based on Newton's law of cooling, and the corresponding differential form is called the Fourier's law of heat conduction. Here, Q is the heat transfer from a heat reservoir at a high temperature Tc to a cold reservoir at lower temperature T, lower temperature T cold. Okay, Tc. R is called thermal resistance. The time rate Q dot, this is a dq over dt of heat transfer, is analogous to the current. All right, V equals Ri. So the temperature difference behaves like a potential difference between the two terminals of a resistor. Potential difference, delta V, is Ri, where I is the current passing through a resistor. The temperature difference is analogous to the potential difference V, okay? It is very similar to the Ohm's law. That's the reason why the algebra of heat transfer is almost identical to the computation of current passing through a register. Okay, that's it.